Hey y'all, Eric here. Welcome back. This is the last video in this series using this little test scene that we've been looking at. There's one more thing I want to go over. It's sort of an extra, but some people might find it interesting. Let me switch over to my main screen here. All right. I want to talk a little bit about hiding seams, blending things together. You see, we've spent a lot of time so far with a lot of these tools trying to cover up the transitions that you inherently get when building a modular scene, which is what this is. Everything, it's a small library of rocks and props, and it's combined together into a hopefully convincing large scene. We spent a lot of time on like making the colors blend smoothly and making like the snow effect blend smoothly and transition accordingly. But one thing I want to talk about is getting meshes to play well together. Let's say I have two opaque meshes like these two. Normally, what you end up having to deal with is hard intersections between meshes. That's just a fact of life in computer graphics. Certain surfaces you can use alpha blending between different surfaces, but that yields a whole other set of problems. But when you're talking about opaque meshes, there's a few tricks you can use on certain types of hardware to make things look a little better. Specifically, desktop hardware is what we're going to be talking about. So hard transitions like this, not the best looking. It'd be better if we could have, say, these rocks here, like you can see going into the ground. That's a smooth transition, right? You can see how the rocks, as they go down, they don't hard cut into the ground. They smoothly blend, right? So that's a technique for mesh blending, and there's a few different ways to do this, but I'm going to try to step through some of this. This might seem like a little bit of a deep dive. I assure you it's not, because we're going to talk a little bit about render pipeline, because everything we're about to cover is essentially a cheat, a hack. It's modifying or manipulating the data that is used by the renderer to trick it into doing what we want. And this is where I think we're going to be covering stuff that maybe a lot of even game artists aren't super familiar with some of this stuff, but it's worth going over, because once you understand what the renderer is doing, you can do all kinds of cool stuff to get what you want out of it. So before we get into what this is doing, I want to talk about the renderer sort of at a higher level. Unreal and lots of other desktop PC games, console games as well, modern games I should say, use what's called deferred rendering, sometimes called deferred shading. There's different, if we get into the nuance of it, there's deferred lighting, which is a separate thing. In general, if you're talking about a deferred renderer, what you're talking about is a method of rendering that has benefits for having lots of complex lighting going on. It runs very well with lots of complex lighting, and I'll explain why. In contrast to deferred shading or deferred rendering is what's called forward rendering, which is what you get on a lot of mobile devices only support forward rendering, handheld devices, that sort of thing. It's easier to describe what forward rendering is. What forward rendering is as a scene is being rendered, each individual pixel of the screen is evaluated for the whole render pipeline, meaning it loads the mesh, it loads the texture, it runs the shader, it computes lighting and shadow, and the key there is the lighting and shadow. It's doing that per pixel as it sort of renders the scene, right? Every frame it runs over the entire image one pixel at a time, and it runs that full calculation. Now, what that means is scenes, forward rendered scenes with lots of lights, lots of shadow interactions, lots of visual effects, lots of transparency. Those get very expensive very quickly, because that cost is accumulated every pixel across the whole frame, and the more, if you have 25 lights in the scene, every pixel, if those lights are, casting shadows, they all have to interact, and it gets very expensive very quickly. By contrast, with deferred rendering, what happens is as the I promise this will make sense in a minute. As the scene is being rendered, rather than rendering out the final resulting image, which seems like the most direct, what it actually does is it renders out to an intermediate series of buffers. Buffers are essentially like textures that it can change every frame. Think of a buffer as just an image, a rendered image that you can't see. We can actually visualize those here in Unreal. So if we just want to look at just the base color, this is called the base color buffer. It is showing me what the just the surface color, or the albedo, it's sometimes called, of the surface is. We can also look at just show me the surface normal. This is world normal. Normal is the facing direction, so it's using colors to represent X, Y, and Z in this case, but it's showing us just the normal direction of the scene. You'll notice there's no lighting, there's no color, there's no highlights. It's just a directional indication. There's also a buffer for roughness. This is the roughness value. Whiter values are more rough, darker values are more shiny. So in a deferred render pipeline, what's actually happening every frame is it's rendering out this series of buffers, and you can even visualize the overview. So this is a shot of many buffers all shown on the screen at once. We got our base color, specular, subsurface if we're not using any, but roughness, metallic, scene depth. Scene depth is an important one. If we go to scene depth, it's in here somewhere, I swear. There we go. This is a black and white image that is showing us the distance from the camera of the surfaces being rendered, right? This is an important one for what we're about to talk about, because in a deferred render pipeline, it renders out all these buffers, and then at the very, very end, it comes in and it does its lighting by combining all those buffers together into a final composited image, and it calculates lighting and specularity and shading and all of that stuff at the very, very end. That's why it's called deferred shading or deferred rendering. It defers the combination of all those things to the very end. The benefit there is you can have many, many, many more light sources, especially if they don't overlap, because as it composites the final image together, it only has to pay attention to the lights that overlap the pixel it's currently compositing. And so if you have, say, a series of light strips along the edge of a theater walkway, right? Those little LEDs, you can actually put a light source along for every one of those LEDs, and for the most part, it's a cheap way to render those lights. You'll get accurate lighting for each individual little spot, and it won't necessarily slow down your whole scene. If you have lots of overlapping lights, you can still get into trouble, but that's a whole different topic. The reason I bring all that up is because this trick that we're doing here, we're able to do because what we're doing is we're manipulating the depth map directly. All right, what do I mean by that? So this is the part where I actually need to explain one more part of the render pipeline, which is post-processing. So as I said, in a deferred renderer, it comes back in the end, it comes around at the very end, and it combines everything into a final image, and it does what's called a post-processing pass, which includes something called anti-aliasing. So anti-aliasing is image smoothing, essentially. It's a way to make images look less hard-edged. If I turn off anti-aliasing, we're actually going, let me just go full screen. I should have done that earlier. You're going to see an interesting artifact happening when I turn off anti-aliasing. I'll let it resolve. Apologies if the compression on YouTube or whatever is not showing this, but there's a very faint dithering happening where those rocks, they don't smoothly disappear. It's sort of a stippled, dithered pattern. I'm going to turn anti-aliasing back on, and you'll notice it disappears. So what we're doing here is we're sort of taking advantage of a limitation in the render pipeline, which is you can't actually smoothly blend two opaque surfaces together. It can't be done. So what we're seeing is actually a cheat. What we're doing is when we're writing those depth values into the depth buffer, we're using a dithered offset. In Unreal, there's a material node called dithered temporal, or dithered TAA, or temporal anti-aliasing. This trick that I'm showing here only works when you're using a method of anti-aliasing known as temporal anti-aliasing. It's called temporal anti-aliasing because what it's actually doing is it's blending the previous frame data with the current frame data. It's accumulating frame data over time or temporally. And by having that noise pattern change slightly every frame, it makes it so that you can't actually see it that well. It visually blends it in. And so this trick only works when you're using a deferred render pipeline and you're using temporal anti-aliasing. It's sort of taking advantage of those realities of the render pipeline. And it's the reason you can't really do effects like this on lower end hardware or mobile hardware. It's in part because there's just not enough GPU power, but it has more to do with the render pipeline than it does to do with the hardware. These are exploitation of the process, I guess you could call it. And of course, by modifying the material values, I can modify the effect itself. I'm going to crank it up. You can see the rocks almost start to fade away. If I set it to 0, you get a hard edge, just like always. If I set it to 2, what that 2 means is it's pushing, using this dithered pattern, it's pushing the depth values back away from the camera 2 units or 2 centimeters. And so I'm very close to the rocks here. And I get this smooth blend. But it's visually, it's enough to convince you, if I get back up to eye level here, you don't see those hard edges. And if I turn it off, you can immediately see it, right? It's like, oh, look, video game rocks. Even a 1 unit offset is enough to give it a little bit of a soft blend. And that's a pretty cool trick. Hopefully that makes sense. This one it's a little bit of a mind bender, but it's super, super useful. In this case, I'm just applying this on these rocks. Sometimes this trick is called mesh blending. Sometimes it's called deco mesh blending, deco for decoration mesh. Sometimes you only do it on certain meshes. You can get a little more aggressive with it. Like for right now, I'm only doing it on these scree rocks, these small loose rocks. I'm not doing it on these larger rocks, but we can, and I'll illustrate that here. So this rock here, you know what? This is kind of hard to see. I'm actually going to disable the snow on these rocks, so we get a little more visual contrast between the two. And then I'm going to enable the pixel depth offset blending, which is the thing we've just been talking about. So here you can see right off the bat, right? I'm just going to toggle this off. We get that hard visible edge between the rock and the snow. Turn it on and it immediately softens. It looks a lot better. Now, there are some side effects. One thing is that depending on your temporal anti-aliasing settings, you can get a certain amount of smearing happening. Like I actually have a node here that will let me change what's called the temporal anti-aliasing frame weight. I think 0.04 is the default. And if I set that to the default, when I move in and out, can you see that weird visual smearing happening along that blend? You can see it kind of regardless of which direction I go. That's a side effect of the temporal anti-aliasing. Remember I said that it has to do with frames accumulated over time? Well, what we're seeing there is the settings are set too low, so it looks nice and smooth, but there's a visual lag as you move the camera around, and that's bad. And it's one of the reasons that a lot of people really hate temporal anti-aliasing. And I understand why, but again, it's the only way you can do certain tricks like this. I like to use a little bit snappier frame update. You run the risk of introducing a little bit of flicker, but it tends to smooth it. If I crank this up to like 0.8 or something, suddenly now you can actually visibly see that dither shimmer that's happening, and it's because we're not using enough temporal smoothing. I need to, like I said, 0.2 is my preferred setting there. Now this is a pretty good compromise. We get the nice blending. We don't have nearly as much smearing. One other side effect is remember, these are two opaque surfaces with their own independent true surface depths. If I look under here, I can see the ground just continues, right? So if I use settings that are too large, like on this one, I'm currently using a blend distance of 10. If I set it to 0, we can see where the true intersection is. Values of like 2 to 5 are really good, and you know, when you're standing it up at this height, they tend to be really convincing. But if you go higher than that, like I'm going to go to 20. Like, okay, that looks cool until you start to move the camera around and you start to see, it almost looks like the rocks are transparent, right? And you can see the ground, the parallax shifting differently. And especially in VR, this becomes a problem because you have stereo vision. You know, your eyes can perceive that these things are blending together. So you got to be careful with it. It has its limits. But we're getting smooth blending. If I turn the snow back on, this hides some of that. But again, we're seeing the pattern. So I'm going to take this down to like 5. That's a nice blend. So hopefully that makes some sense. There are a couple other side effects too if you get too aggressive with it, especially larger scale. Like here we're you know, looking at surfaces that the player would be right up against. But if you want to use this technique sort of in a macro sense, like if we were doing more of a landscape and we wanted big hills merging into other hills, there's another area you can get into trouble too with large values. So I'm going to take the distance and crank it to like 20 or 50 even. We're getting lots and lots of smooth blending, but there is a side effect to go with this. Let me turn this off and turn it back on. I'm just toggling the pixel depth offset blending on and off. And what I want to point out with these large values, I'll back up so you can kind of see it a little clearer. Look at the overall lighting. You'll notice the rocks get way darker, especially this one in the foreground, the rocks in the background. When the effect toggles on, it gets really dark. Why is that? Well, the reason for that is, remember, we're manipulating the depth buffer of the deferred renderer directly. We're cheating it by pushing pixel values back, and in doing so, we're actually kind of breaking one of the foundational things about a deferred pipeline is that it's going to do its lighting at the end. It's using this depth buffer, and it is it's because we've manipulated it too intensely. It's getting some incorrect lighting data, and it's treating these surfaces as if they are shadowed. Again, this rock is a good one. If I toggle this off and on, you can see the shadows even disappear. So there's a way around that. And it's a further complication of this system, and it's actually using the mesh data itself. So there's another technique that you can use in Unreal and other engines, which is it's something called mesh distance fields, or MDF, not to be confused with medium density fiberboard. That's a different thing. Mesh distance fields are a let me just open one of these meshes up here so we can see what we're looking at. So this rock, right? It's a mesh. It has a hard surface, but we're generating what's called a mesh distance field from this, which is, I don't think, let's see if there's a view mode in here. I don't know if there is. I don't think so. No. I can do it in the main scene. So what a mesh distance field is it's a pre-process that runs on a mesh, and it generates basically a volume texture. If I can visualize mesh distance fields, there we go. So these weird ghost meshes that exist, what I'm doing is I'm visualizing the mesh distance fields on each of these individual rocks, and you can see they almost have like a aura around them. A mesh distance field is a form of signed distance field, which is a volumetric way of storing data that tells you, it basically builds a low resolution gradient around surfaces that store the direction of the surface and how far the surface is away. And they are very useful. You can use them for shading and shadowing and ambient occlusion and all kinds of cool stuff. But in our case, if we want to fix this issue that we're running into, we can use these mesh distance fields to correct them. It gets a little more expensive in the shader, but it is a way of doing it. These are the individual mesh distance fields in Unreal. These get combined into what's called a global distance field, which we can also visualize. Turn that off, turn this on. This is a global distance field. What this is it's basically combining all of those individual mesh distance fields into one unified field along with the landscape geometry. I can toggle back and forth between the two so you can kind of see what we're dealing with. And all of this is to say we can access that data if we would like to. So I'm going to go back to my material, and I'm going to enable a material feature that I've written into the shader that does the same pixel depth offset trick we were just doing, except I'm going to enable it. Boop. Except you'll notice the lighting pop back in. Now it's isolating that effect to only the areas that happen to be near other surfaces. And it does that by sampling that global distance field that we were just looking at. And so by doing so, it's basically saying, hey, when this rock gets close to the landscape here, go ahead and start adding in that pixel depth offset effect. But as it gets further away from the surface, don't do it. Right, because I don't want to mess up the lighting here. I want that lighting to stay good, and I kind of don't care if the lighting gets a little weird towards the base. And remember, I have this value, the blend distance value, cranked. It's at 50. So that's one way you can mitigate that effect, is by toggling the usage of mesh distance fields on and off. But that does come with a fairly non-trivial cost. I want to say it's, in this case, my shader instructions are going up by about 70 instructions, which is significant, but depends on the usage. But if I were trying to do like a distant landscape with this effect, maybe on just those meshes I would enable it, keep it as cheap as possible. But hopefully that makes sense. And in return, we get the ability to smoothly blend surfaces together. So I think that about covers it for this one. Let me switch back here. All right, I think that's going to do it for this little series of behind the scenes shorts, I guess. This was a lot of fun. I really, really enjoyed doing it. I hope that it was entertaining for people, especially, aspiring game devs or other people who are doing this kind of work. I love doing these little dives and talk and shop, I guess. Thank you so much for tuning in. Thank you for your patience, especially the backers. I know you guys are waiting for the game, and we're working hard on it. It's going to be awesome. This last year was a year. But we're doing good. We're doing good, and I'm very, very excited for the upcoming year. And yeah, I don't know what else to say. Be well, be safe, and we'll talk to you soon. Thanks, you guys.